Next up, we have Celina Brule, our sole Autonomy College participant tonight. So she's representing. She is a chemistry student, and her title, Fighting Corrosion with Chemistry.
Corrosion. It's something we see every day, on bridges, buildings, cars, even in places like the playground. The cost of corrosion is high, over $100 billion annually, so we try to stop it from happening. One of the more efficient coatings out there is based on chromium-6, but in order to prevent corrosion, it slowly leaks this chromium, which is carcinogenic and can easily enter us and the environment. So there are a lot of limitations out there for its use. We are working on making an alternative to this coating using two things, a UV cross-linking sol gel and a conductive polymer called polypyrrole, both using green chemistry principles in their synthesis. You can think of the sol gel as a barrier. It has a silicone backbone and can be customized like Lego for any application. The UV cross-linking makes it extra durable. Think back to being a kid and playing Red Rover. When you all linked arms and a kid tried to break through, it was really hard. That's essentially what the cross-linking enables. When the coating is exposed to strong UV radiation, it causes the siloxane network to link together and create a huge cross-link barrier. But this is just like a wall. What happens when it breaks? What happens when that kid gets through? This is why we're incorporating a conductive polymer to improve performance of the coating. This class of polymer has a lot of double bonds, which act to prevent corrosion at the metal surface. Corrosion is chemistry, and it relates to the movement of electrons. Think of the electron as a hot potato. If you're the only one to hold it, you're going to drop it because it's going to burn your hands. But if you were able to pass it along to someone else, and that person can pass it on to someone else, it takes a lot longer before it gets dropped. This is what the double bonds in the polymer enable, the passing of an electron. In this way, even if something happens to the Red Rover line, there's still a chance to prolong corrosion, which the sol gel can't do on its own. So we've made the sol gel and we've put in the polymer. Now we need to see if our hypothesis about better performance is true. The last step is testing it, and we want results quickly. To do this, we immerse the coated pieces of steel in a solution designed to act as an extreme prolonged exposure. It doesn't directly give us the results in normal conditions, but it shows us fast if our coating is any good. To get data that has meaning, though, we need comparisons. So we do this test on slides with just the sol gel and with the polymer incorporated. The slides on their own corrode almost immediately. The moment of truth. Does our coating with the polymer outperform the coating with just the sol gel? The preliminary results would indicate no, they perform as equals. But does this mean we failed? No. Some of the data we have on our polymer suggests it might just have low conductivity, meaning less of the ability to pass along that potato. So we have a new question. Would incorporating a more conductive polymer increase the performance of the coating? But what is science without the scientific method, or research without more questions? This isn't the end of research on this area, only the start.